Hello, everyone. I'm Terence from Hong Kong University of Science and Technology. And today my presentation is about the OpenBeam and blockchain-enabled full lifecycle carbon emission management framework. And firstly, we will discuss about the background. And for the current situation, the buildings and the construction industry represent the 37% of global operational energy and process-related carbon emissions. And also, Hong Kong government have some plans to do that. Like they want to make sure that in 2020, the 2030s, there's 11% of the reduction about the carbon emissions in the construction industry. And also there's a lot of carbon emission management method is required in the globally, like the World GBC and also the HKGBC and something else. And so based on that, we want to discuss what kind of the carbon emission should we management or should we pay attention to. And so we use LCA as a background. So in here, our project will discuss two stages of the LCA about the carbon emissions. The first part is the A stage, which is the cuddle to sit. And also the second, the B stage is the building usage. Like it's after the construction stages, the building is under use. So of these two different LCA backgrounds, the carbon emissions takes the most part of construction life cycle. So we will mainly discuss of this part. But still, there are some problems in the carbon emission management. So we find that the first part is the exiting the beam-based embodied carbon classification is not automatically enough. The embodied carbon is LCA stage carbon emissions, and also in the construction progress, there's still lack of the guidelines and the standardized practice to collaborate the construction carbon assessment. And the last part, in a commercial world, and the carbon emissions need to be tracked, and we need to make sure the data, the flow is completed and which the carbon emission come from and which part we can reduce. So the integrated platform for the life cycle carbon quantification, compensation, and tracking platform is still needed. So based on that, we developed some methods. We developed open beam based and blockchain enabled framework to do that. And for the first part is the open beam and also the Dynamo-based tool for the automated embodied carbon quantification. For the second part, it will be the open beam based collaborative model the beam information enrichment, and also the automated tracking. And the last part is open beam and OpenGIS with the blockchain to make sure the carbon assessment tracking can be finished. So this is our methodology framework. It shows here. And I will discuss this part partly. And for the first part, like we should need to know what kind of the carbon emissions, like the embodied carbon, or what kind of carbon emissions come from. So we developed this ontologies. We can see the A1 to A4 stage is for the materials developed and also the transportation to the construction site. And also the A5 stage is in the construction site, what happened here. And the carbon emissions the source is shows here. And also for the B stage, the operational carbon, we also have an ontology, which we can see the mainly from the HVAC, the integrated heat gain, and also the building itself, and also the weather. So using these four different kind of parts, we can track all the operational carbon in the building's life cycle. And then we firstly developed the Dynamo plugin for automatic embodied carbon quantification for A1 to A3 stage, which is beam-based. And we can see the family type for carbon is have the 10 of them, and we can use this to automatically get the results. And the validation part we'll say later, which we have actual cases. And also, we want to make sure that the beam exchange process identification can be fruitfully, like we want to check the data exchange requirements, is it meted? And also for the further carbon emissions data tracking can be done. and which we developed IDM, the information delivery menu, which to improve the communication and data exchange quality. And all this kind of data, after the checked, we will put them into the blockchain system to make sure the carbon-related data can be tracked using that kind of system. And then the operational carbon emission quantification for the B stage is just here. We also use the data we developed and checked in the last step. And then we use the boat and also some Python energy simulation engine. Like in here, we use the eQuest. And some other scenarios, we will use Energy Plus. And the developed method can directly use for this kind of different energy simulation engines. And then for the last part will be the blockchain, the OpenBeam and the blockchain integrated platform, which have 4 different functions. The first is the OpenGSpace A4 stages embodied carbon quantifications, which A4 stage is mainly for the transportation of the construction materials. So we use OpenGS to automatically get that kind of data. And also we have the design and actual embodied carbon comparison and virtualizations, which we want to make sure the beam-based carbon-related the carbon emissions, and also can compare with the actual set, the construction set provide us the carbon emissions, like which is from the supply chain and also which from the state itself. So we can use this part to give us to make the carbon-related management can be more friendly and the data can be more actual. And for the third part is the operational carbon data simulations, which we use the knowledge graph as the baseline and use the single source for the information for both stages and dynamic data, which can make sure for 1 year, the data, the operational carbon for this building can be directly calculated and quantified. And this is the third functions. And for the last one will be the blockchain-based embodied carbon footprint tracking, which we developed the smart contract for that, and which can link to the FC files and also can directly check some data in that. And then is our validation part. So for the first is we use the OPARC 2, the original resource recovery center in Hong Kong to test our proposed framework is available or something else. And so we firstly prepare the basic data, like the embodied carbon and the beam models, the FC files, and the standardized FC schema for support thermals, and also some basically information shows here. And we use this information to firstly get the embodied carbon quantification, which is for A1 to A3. And in here, the Dynamo plugin can automatically give us the total results about the carbon-related data from the beam models. And then in the construction setting, we also have a FC extension algorithm, which the original FC files can have some actual material type, which is in the construction set or the supply chain part. And in here, we can get the actual material type, actual material emission factor, and also the actual material regions, which can provide us more information like in A4 or A5 to make sure the embodied carbon quantification is real in this step. And then we want to make sure the communication in the different departments in a construction set can be fluently, and we want to make sure that all the data for the carbon emissions is true. So it's useful for our framework. So we developed this automatic checking with IDS. We can see we have already set some IDS rules based on the US beam, and also the checking using this beam models can say it have the embodied carbon related data, or it have the transportation related data or something else. So in this way, we can make sure the FC files or the beam files, the beam models is available for the carbon management. And then the smart contract in the carbon emission management framework is here. We will upload design the carbon result from Dynamo, which is directly from the beam models. And also we will use IPFS to set the IFC files, which is enriched with the actual construction data is here. And using this way, we can make all the in different kind of supply chain steps or in different stages of constructions, the carbon related data can be tracked by this way. And we can know that what kind of carbon emissions from the different department, from the different regions, or from the different part of the building. And then the last part is the blockchain-based carbon footprint tracking. In this here, we also using that smart contract to make sure the carbon emissions reporting and tracking can be done. And the integrated with the blockchain platform which is work for FCs. We can see it have three different virtualization methods. The first is actual construction carbon emissions. Also, it has the design carbon emissions, and the last part will be the actual carbon emissions here. And then in the platform with the OpenBeam with the blockchain, we can set the A4 part, the embodied carbon quantification in this framework is based on FC files. And in here, we can directly get the transportation distance, which is 70.7 kilometers. And then for the operational carbon part, the developed method can also keep the consistent with the manual modeling, and we can get all the carbon emissions in 1 year. And the model development is reduced to 99%. And the carbon emission results it shows here. The first part, we can get the different carbon emissions in A stage and the B stage. All the results shows here, which by this framework, we realize the construction lifecycle carbon emission size and the tracking based on the OpenBeam and blockchain. So, and then the last part will be the conclusion of our developed framework. The first part is setting the beam-based embodied carbon quantification is not automatic enough. So based on that, we propose that OpenBeam and blockchain-enabled full lifecycle carbon assessment tracking framework, which we can get the embodied carbon, the operational carbon, which we call that the lifecycle of the buildings. So based on that, the carbon emissions tracking can be done. And the second part is the lack of guidelines and standardized practice to collaborate. So based on that, we developed the embodied carbon data enrichment tracking approach for BEAM, which we have the IFC enrichment algorithm, and also we have the IDS tracking automatic method. And for the last part, commercial world needs to make sure the data security, and also we need to make sure what kind of carbon emissions come from. And so based on that, we can to make more strategies to reduce them. So based on that, we developed a smart contract to support the operation of the carbon tracking in the framework. And based on that, we can achieve a efficient full lifecycle carbon management and tracking method for the construction. But still have some limitations like the design, the IDS was not comprehensive for the complex real-world construction, and also the dynamic feedback of the carbon emission management is not realized in this process. So maybe in the future, we will develop some method based on the blockchain and digital twin to construction set digital twin to make sure the carbon-related management or like something more the stabilization part can be realized using this kind of method. And thank you very much. This is my presentation.